All right, so now, what is Aaron? Aaron, can you share the screen? Can you share my open math? And I'm going to annotate. Okay, so let's, are you guys already, this is the second question here. So let's see. I'm gonna choose to annotate. This thing kind of goes away. Okay, so then the question is, so Aaron, can you go to the other assessment? So go to that, click there. Independence part 1. Okay, so for linear dependence or linear independence, we want to consider a very particular linear combination, which is analogous to a homogeneous system, right? So if we have, in this case, a set with 3 vectors, they're called u, little v, and w. Well, they're all little u, little v, and little w. Then it says, can you find w such that the set u, v, and w would be dependent?
How do we do that?
How do we do that? A couple of ways. Very, need a color, so maybe this color works. Okay, so how about alpha 1 u, alpha 2 v, alpha 3 w? So when we're talking about either dependence or independence, what we are saying is that this linear combination would be equal to 0, 0, 0.
But it's once it.
So when we are going to refer to, is this set of vectors independent or is this set of vectors dependent? We need to represent a linear combination of the vectors under consideration, a linear combination that equates, that is equal to 0. That's called the relation of linear dependence. That linear combination equated to 0. And that is the analogy. This is another name of this would be, this is equivalent to a homogeneous system, and we're interested in the solution set of this homogeneous system. So that solution set, right, there are 2 choices here, one with unique solution, and in that case it would be trivial solution, that means all zeros, and another case with infinitely many solutions. So either it has one solution only, in which case it would be all things, all variables, alphas or x's, they're all 0, or there are free variables and then dependent variables, and there are infinitely many solutions. Okay, so if we are in the uniqueness scenario, this would be considered independent. If the only solution is a trivial solution for that homogeneous system, then we would consider the u, the v, and w independent. But if there are infinitely many, which means that that includes having non-trivial solutions, then here this would be dependent. And this would include non-trivial. Would include non-trivial. So, in other words, that can you, if you set alpha 1 to be 0 and alpha 2 to be 0 and alpha 3 to be 0, then of course you're going to generate a vector of zeros. But maybe one of the alphas is 0, but the other ones, they're not all 0, right? So that would be a case of non-trivial solution set and therefore dependence. So another implication of having a set of vectors that is dependent, in this case, the set only has three members. So another implication with this dependency is a sense of redundancy. It's as if some of the vectors are redundant. What is redundant? Guys, can you guys tell me what is redundant? How do you explain redundant? Unnecessary, that would be one thing. Repetition is like something is repeated. Would be another. What else? What are other words for redundant? Excessive. If something is in excess, it's also repeated in a sense. So that redundancy, which is like a fingerprint or footprint of dependency, it's in the sense that some of the members are multiples of the other ones. And in that sense, they are repeated. The other sense of being repeated is if not only they are multiples, but in fact, they are linear combinations. So you could have partial linear combinations. So you could have one of the members being a sublinear combination of the other ones, and that would make the whole set dependent. And in that sense, there are repetitions, okay? So the way this is phrased, find W that would make the set dependent. If you take a linear combination of U and V, you can find that W. Let's try that. So, but you choose. So everybody, how do we make a linear combination? Everybody chooses. So it chooses a different, so what you have to do is take U, 5, I'm gonna say here, U is 5 minus 3 minus 3. And this has a scalar there, and take V, 1, 1, 3. And this has a scalar in front of it, okay? Everybody chooses, well, you have different vectors, but you choose what those scalars are. You could choose 1, 1. You could choose 1, minus 1. You could choose minus 1 first and positive 1 second, right? Choose scalars that are non-zero. And then that generates a new vector, which you would call W. That's the vector you write there. So that's one way. Let's do this. Do it on paper. Write on paper. And you write your U and your V and the scalars you chose. And I'm going to display your paper in the camera in a few minutes.
So I have a question. Is W, when if we're finding a linear combination of U, V, W, are we saying U plus V equals W? Is that one way of determining it?
U plus V, it's almost that. Yes. It's almost, because if we say U plus V, that means 1U plus 1V equals W. So that would be one special case of one specific linear combination where the scalars are 1 and 1.
Okay, so in that case, is that what we are doing to solve for this? Or?
Yes, yeah, something like that. But you can take other multiples.
So it's in the so we're turning into an augmented matrix. U and V are the variables, and W is the solution.
Okay, so that's a good. I think if I'm following you, I'm gonna make a choice. So you said 1 and 1. I'm gonna slightly change that. I'm gonna say 1 here and minus 1 here. Okay, just for the sake of finishing this. I'm also helping Aaron. Aaron, are you with me? Maybe. I don't know. But so since I'm running out of space here, so I'm gonna, this is kind of weird, but I'm gonna write this is a new vector, which in this case is very simple. 5 minus 3 minus 3, nothing changes. And this here would give a new vector, which in this case is the action of this. No, this becomes minus 1, and minus 3. Is that right? Yeah. So then when we add these two, we add them together, right? We have 5 minus 1, that's 4. Minus 3 minus 1 is minus 4, and minus 3 is minus 6. So that's what we should write here as 4 minus 4 minus 6. So Aaron, can you enter those numbers and see? Thank you. Okay, how do you submit answer? Submit. it's complaining because the other one is empty. Is that right? What? Yeah. So okay. So Aaron, just hold on a second. Let's say find W that would make an independent set of vectors. Okay. So once we have constructed this W is new, and we constructed it in this way to confirm linear dependence, we could assume that we don't know if they're dependent or not, even though we know it because by construction, that's how we set up W. And if we don't know, we could use RREF, right? So in this case, you could, if you pretend that you assume that you don't know, you could form an augmented matrix with this as the first column, this is the second column, right? So you could say I have 5 minus 3 minus 3, 1, 1, 3, and then the last column, you say I have 4 minus 4 minus 6. So Aaron, can you row reduce this with one of your RREF calculators? Okay, that. Mm-hmm. Okay, so these RREF would be telling you that are they dependent or are they independent?
To the RREF model, it says they're independent, but the way we generated it, it's supposed to be dependent.
So this RREF is contradicting our expectation, isn't it?
Yeah.
Hmm.
Maybe type something in incorrectly.
Let's see. Aaron, so scroll up here. There's something that's not right. So maybe my
It's negative one,
arithmetic.
negative one, negative three, no. 1, 3.
No, but
You want
the
negative one, never mind.
Yeah, it doesn't
That doesn't make sense.
I think he missed it.
And he hasn't put in right.
Yeah, what's in the bottom
I
line?
think it should be negative one, negative 3. Not 1, 1, 3. It should be 1, 1, 3.
Hey, when I did it, I didn't get a contradiction.
oh
Negative.
wait,
No, it still should be 1, 1, 3. No, because the original vector is 1, 1, 3.
the original vector is 1, 1, 3. So that second column is, but the first column, what
5, negative 3, negative 3.
is the last one? Negative 3 or is it positive 3?
It's fine.
That's probably it.
It's written down.
First one is first one's -3.
That should be minus 3, Aaron. Maybe that's what you got. So do it again. And again, you have
So it may be the calculator.
really? Well, let's try another calculator.
I can verify it.
Hold on a second. Okay, so let me check.
Okay, that one's right.
Yeah, see that? And I guess it's just a calculator.
Calculator.
So you guys found another RREF? That's correct. Okay, Aaron, so that's correct. So the answer, what is this? Is that, uh-huh. Okay, so there was, the calculator was tripping us, right? So we were trusting that first calculator, and which is similar to what happened to you, Trevor, maybe, in the previous problem. So with this RREF, which Aaron, on my end here, I use Wolf and Alpha, and then I confirm, right? So with this RREF, you can, then with this RREF, you confirm that there is no contradiction anymore, and in fact, that the values that what this would say here is that what you infer from the first row here is that you have 1 alpha 1 equals 1, and then the second row implies that 1 alpha 2 equals -1, which were exactly the values that were used to build and construct that W. So we went backwards and we confirmed. This is one of those problems where we had the answer. We knew, right? We were just trying to confirm. Okay. So, okay, this is how you build the dependent. So, Aaron, let's go back to the question. And I need to, I'm going to close this. And this is messy. Clear. Okay. So, all drawings.